All right. Yeah, I think my screen is sharing, right? Oh, sorry, there's some voice back. Is very limited comparing to the central cloud data center. While there are a lot of devices and also many data being produced and processed in the edge. In the middle, it's basically the edge of the core network, or we understand it's kind of edge of the operator's network. So in this location, the applications might be different, like people want to run their live streaming, webcasting there, or run some gaming like VR games server side there, and also doing some online education. So in this location, if we also look at the AI perspective, there are a lot of like transcoding applications running there. So around 30% AI inferencing will be done there, because the most of the inferencing applications are running in the end user side. All right. The central cloud I think we are quite familiar today. The applications can be quite different. So we can run AI training as well as some well-known the AI inferencing in the data center, and also we can do transcoding. So one common understanding that is from the central cloud to the edge, the hash rate and the underlying hardware architecture are quite different. So in the central cloud today, they are more based on the x86, right? And also, but on the edge, they are different. So we know that the ARM-based hardware need less power supplement, right? And also there are some of the smaller x86 hardwares can be running there. So the hash rate is quite different, and also the underlying architecture is quite different. So the major consideration why we build a edge platform on top of Kubernetes, why we choose cloud native technology to build, is that actually I think the benefits are quite well known already. The Kubernetes are using containers as the core pieces of a application. We know that containers we just need to build once, and it can run everywhere. And also the container image have different multiple layers, so we can easily optimize the base image layer to reduce the image size, and as well as the system of overhead of the application. And also Kubernetes today, we all believe that it's already a de facto standard of the application abstraction, especially in the cloud. If we can use the cloud native technology to build the edge computing platform, and also build the platform across cloud and edge, we can get a very good experience that we manage the applications in the cloud and on the edge with the same experience. And also for Kubernetes itself, we know that all the applications are only talking to the API server, right? And also they have the Kubernetes itself have the declarative API, and also it supports multiple group of API and the different API versions, and also have the extensible functionality like CRD. We can easily extend the API if we need some more new abstraction on the to run the applications on the cloud, on the edge. And also for Kubernetes itself, we can easily to add new components, like we use the build the operators for some customized applications in cloud today. But there are still some challenges. So one big challenge is that, especially for industry and IoT, the edge nodes are, the resources on the edge are quite limited. So for a vanilla Kubernetes, even a lightweight distribution, we know that it needs at least 1 gigabyte, right? And also, like even we try to install kubelet on some of the edge nodes, kubelet itself needs more than 100 megabytes, while we know that on some gateway node on the edge, in total it may have like 128 megabytes or 256 megabytes. So the operating system itself also needs some memory, and also if we run the container runtime, it takes, for example, container D, it needs at least 70 megabytes. So the resource limitation is one of the biggest challenge to manage the applications on the edge. And also the edge and the cloud. Between cloud and the edge, the network environment is quite different. So in many cases, the edge may locate in a private network or behind a firewall. It has very limited bandwidth to the central cloud, and also the latency is quite different in different cases. It's not guaranteed latency comparing to all the nodes communicating with each other inside a data center or inside a cloud region, right? So the network is quite unstable, and also one of the big motivation of managing the applications on the edge is that we want to deal with some of the business serving on the edge, right? It make it able to process some of the requests on the edge directly to save the end-to-end latency. And besides that, we also want to the edge have some of the autonomy capability, so they can manage the application themselves. I mean, when some disaster occurred and recovered, the edge should able to recover the applications themselves, not rely on the central cloud to recover all the applications. And also the edge may, in some cases, the edge may get offline for quite a long time. So it definitely it would break if we always rely on the central cloud. And also on the edge, we know that the edge nodes have very different client architecture. Some are based on the ARM, and some are based on x86. And also, especially for the IoT devices and the industrial device, they are very different devices, and also they have very different device protocols. So for the end users, if they want to develop the applications on the edge, they need to deal with the multiple different device protocols. it adds the complexity of developing a application. So Kubernetes and the cloud native technology today not yet have a very simplified solution of speeding up the application development. So that's also the another big challenge. So with that background analysis, so KubeEdge, we think that first of all, we definitely want to build based on Kubernetes as well as the general cloud native technology. And besides that, for especially to the cloud and edge coordination cases, we think that we have 4 aspects of the enhancement. First of all is KubeEdge provide a seamless cloud and edge coordination mechanism. So basically, even if the edge nodes are located in private network or behind a firewall, or if it doesn't have a public IP address, it's okay. So the bidirectional communication terminal itself will deal with the upstream and downstream synchronization, and it supports both metadata and the user data. And also for edge autonomy, KubeEdge introduced the node level meta persistency. So even if it's disconnected to the cloud, the edge nodes doesn't need to wait for the list watch response from the master. It can recover by itself. So it's getting ready faster, and it saved the bandwidth between cloud and edge. By the way, for the general architecture, there are 2 types in the ecosystem. So one idea is that running the whole Kubernetes cluster, or maybe a lightweighted Kubernetes cluster on the edge. Another one is putting the nodes on the edge. So KubeEdge started with running nodes on the edge because we think that it's easier to do the resource optimization for the very limited use cases, and it's easier to coordinate with the central cloud. Okay. For the resource restriction, so what KubeEdge optimized is that it removed some of the irrelevant functionalities, like the cloud provider storage integration. Because on the edge, we definitely have a very different storage type. So also because we introduced the node level metadata persistency, so we kind of replaced the static part functionality to make it read from the local metadata. So like in KubeEdge 1.3 itself needs around 70 megabytes when it started up. And also KubeEdge supports the standard CLI interface. So it's easy to integrate with Containerd. So Containerd needs around another 70 megabytes. So then if we add the system overhead of the operating system, probably a edge node can, for the end user, they just need like 112, and they can have a lot of resources to run their own applications. And also for the CRIO project itself needs around 30 megabytes. then we can even run KubeEdge on an even smaller edge node. So that's quite valuable to especially the resource constraint situations. And also for the edge device communication, KubeEdge introduced a extensible framework to make users able to define their own device protocol. So, and also for the underlying framework, KubeEdge provides a device mapper layer, so it helps convert from the actual device protocol to a general protocol. Currently, it's MQTT. So for application developers, they just need to rely on MQTT, and they can talk to all the devices on the edge. So that helps a lot for the end users to build their applications on the edge, especially when dealing with multiple devices that consist of different protocols. All right, so this is a very general overview of the KubeEdge architecture. So it have basically three parts. So one is on the cloud, the central in the public cloud data center, and also one is on the edge, and then another one is about the devices. So in the cloud, if we look on the left, it's quite similar to the vanilla Kubernetes. So we know that Kubernetes manage all the resources as objects, right? Any status change would finally reflect on the object status. So what KubeEdge did is that we have a CloudCore to deal with all the stuff on the edge. And we do the shadow management inside Kubernetes. So for Kubernetes, it can find some node marked with a label that is located on the edge. But actually, we know that the scheduler just see the node objects, and they just see there are some pods to get scheduled. So they will do as usual. And the CloudCore will watch all the resources that are relevant to the edge, and it will help to dispatch all the updates to different edge nodes. So today it contains, from a user perspective, it contains edge controller, device controller, and the cloud hub. But inside there are more other modules I will introduce later. The bidirectional communication terminal, today we are relying on the messaging over WebSocket, because we know that WebSocket supports both upstreaming and the downstream with one connection. And also we support the messaging over QUIC. The WebSocket implementation today is more reliable and has better performance. So it's the WebSocket is still default now. All right. So at the edge, the most important are the EdgeCore. So besides lightweight kubelet, we also have a node level metadata persistency, and also we have the we actually have a edge hub that's symmetric to the cloud hub to deal with the messaging stuff and the bidirectional communication. And also For the container runtime integration, we support a standard CLI, so it's easy to coordinate with either Docker, Entity, or Clio, or other runtime. And also, we support, because we support CLI, we support CNI. And also for the CSI, it's easy to integrate with the CSI on the edge. KubeEdge itself, we introduced some CSI plugin to hook the request to the edge, so users can just integrate the existing third-party CSI implementation, and they can have the same experience managing the storage on the edge. And one of the big challenges is that if we have a very big deployment and highly distributed, so we may have our edge nodes located in multiple edge, edge sites. So that means that the different edge nodes may locate in different private networks. The network environment is quite different with the those in the data center, right? In the data center, in the cloud, to Kubernetes, it's actually a very simple network. Each node can talk to each other directly based on the node IP, because they all located inside of the same VPC, right? If we run it in the public cloud. But in the edge computing cases, it's quite different that the edge nodes may locate in different private network. So first of all, the edge nodes cannot talk to each other because they even don't know which IP address is reachable to that node. And also for the pod networking, the big challenges are how we install the CNI implementation, because almost all the CNI implementation today relies on the data center networks. And also, on top of that, how to deal with the service and the other ingress. So today, the basically idea is that KubeEdge want to reuse the service mesh idea. So basically, Kubernetes cluster in the cloud, and also you have some nodes on the edge you want to manage, and also you have some of the devices you want to manage from the end. But actually, this whole texture is very flexible. If, for example, in the manufacturing cases, the factory may not want to have their data in the public cloud. They want to hold on-prem deployment. Then they can actually just install the Kubernetes. They basically currently the part marked with cloud in their central room in the factory, and also they can have the edge nodes in different workrooms, and also the networking between the CloudCore and EdgeCore. They don't need to have the wired network. They can just rely on wireless like Wi-Fi or 4G, or we know that 5G is definitely better, but if even it's 4G is okay. Okay, and also they can have the devices on their product line. So the whole architecture is quite flexible. Really depends on how the end user want to deploy that. So the CloudCore. So the CloudCore itself is actually just doing the shadow management of the stuff, the resources on the edge. We know that for a standard vanilla Kubernetes node, each kubelet will update the node resource as well as pod that's running on that node to the master, right? And on the for edge computing devices cases, the difference is that the edge nodes are located on the edge. So CloudCore here will hook all the updates and then distribute it to the remote nodes. Inside CloudCore, currently we have the 5-part, basically 5 modules. We actually want to reduce the number of processes to make it easier to deploy and manage. So edge controller, device controller, and sync controller are in one process. They can be deployed as a pod. And also the Cloud Hub can be deployed as a pod in Kubernetes. So edge controller is a shadow management for actually the Kubernetes core APIs, especially the node, the pods, and also config map or services, right? And also the secrets and endpoints. So the device controller, so actually for the industry and the IoT cases, KubeEdge provided a set of the device API, device CRD, to simplify integration with third-party device protocol. So the device controller here is responsible to deal with the device CRDs, the life cycle of the device CRDs, and also it's responsible for the shadow management of the real IoT devices on the edge. For the sync controller, it's actually a helping controller. It's responsible to deal with the consistency. It will periodically check the status in Kubernetes and those successfully persisted on the edge. If there's any inconsistency detected, it will trigger the reconciliation. And also this is very useful in the disaster recovery. So the system doesn't need to check the whole things. They just need to check the current status between cloud and edge. And KubeEdge CS driver here is actually a plugin to hook the storage provisioning, etc. Oh, sorry, my. Hello. Sorry. There were some network issue on my side. I'm back now. Let me share my slide. Okay. So the admission webhook here is dealing with the CRD validation, and also in the longer term we will integrate the best practice. For example, we know that Kubernetes by default it will mark all the node unreachable. If the node is disconnected, it will mark it to unreachable status and evict all the pods. But in the edge computing cases, we know that the difference is that even some of the nodes are offline. It's kind of a expected status. So users should be able to customize the eviction period of time, or how long they want to they want their application stay on that node. That's one of the scenario. And also like other scenarios like that. So even for example, the a set of node is offline, but the pod may the one of the edge node may get crashed when it's offline. Then the pod needs to be moved to a healthy node in that edge site. Then when it come back, there are data inconsistency between cloud and edge. In that case, we cannot simply synchronize all the status from cloud to edge, because it will cause the pod eviction again. So in the longer term, we will enforce the best practice in the relevant edge computing cases inside the admission webhook. So here is a little more detail about how KubeEdge make it happen to able to manage a remote node on the edge. So this, when I think you all guys are very familiar with that. It's actually a diagram how vanilla Kubernetes spin up a application. So like the workload controllers, we know that it's dealing with the workload API lifecycle management. So it basically fetch the workload like deployment, updates, and also update the number of corresponding pods. And also for scheduler, it's actually just keep watching the unscheduled pods and schedule them to some of the nodes. And also for kubelet, each kubelet just watch the pod scheduled onto its corresponding node and manage the pod lifecycle after schedule, right? So if you look at all the labels marked with 0, it basically tells us the when the system spin up, right? The controllers, the schedulers, and kubelets will create watch to the API server, right? With their filter, with their own filters, right? And also, then, for example, we say that a end user created one deployment with the kubectl command, kubectl create with the deployment YAML, and also the underlying etcd interaction. Etcd interaction, it's basically just persistent in the metadata updates, right? So once the deployment YAML is submitted, it will be stored in the etcd, and then API server get notification from the etcd the deployment is created, and then the deployment controller get the notification that deployment is successfully created, and then the deployment controller we know that it's actually creating the replica sets, and then replica sets create the number of pods, right? And then the pods get persisted, and then the pod API server forward the notification that pod successfully created to the scheduler, and scheduler will schedule pod according multiple scheduling policies, and finally update the pod spec, right, to fill up with a node name. We call that binding, right? Bind the pod to a node, and then the specific node, the kubelet will get the update that pod is bound. Okay, so it will spin up that pod on that node, create the containers, create provision the container network, and also the container storage, right? And so what KubeEdge hooked in this lifecycle for pods is actually is actually the step outlined here. So how KubeEdge works? In this case, actually, after the scheduled a pod, it's not directly the kubelet got the notification, but the CloudCore. So actually, the Edge controller got the notification. So actually, Edge controller will get all the pod updated notification, but it will filter. It deal with only the pod that are scheduled to the Edge nodes, right? Because the Edge controller had know everything, so it can easily to filter the Edge nodes by name and get the corresponding pod, and then it will build up with a message and let the Cloud Hub to send the notification to the corresponding node. So here, the reason why we have a Cloud Hub and Edge Hub here is that we know that the Edge nodes may locate in a private network. It doesn't have a public IP address, or it may be behind some of the firewall, right? So actually, the when the system starting up, the EdgeCore is actually starting the communications. It will request to the CloudCore to build a bidirectional communication tunnel, and then it will the tunnel will keep there, and once the pod updates come, the Cloud Hub knows that, and it will send the message to the corresponding EdgeCore. All right. So when the EdgeCore or the Cloud Hub got the notification, first of all, it will let the Meta Manager know. So Meta Manager here is basically a node level metadata persistency. So for the metadata storage backend here on the Edge node, we are using SQLite currently because it's kind of only actually caching the nodes informations on the node. So SQLite is a very lightweight and simple storage for database for storing like the metadatas. If any inconsistency happen or if it's broken, we can still synchronize from the central cloud, from the Kubernetes API server, from the etcd, because there they have the whole set of the data there. Right. So at the end, when the persistency succeeded, the Meta Manager will forward the event to the HD. HD is actually a lightweighted kubelet, and the HD will spin up the pod on the node. Okay, so actually, if you ignore the CloudCore steps in the middle, it's actually quite similar compared to the vanilla kubelet behavior in the cloud. Right. So basically, we added a few more steps to forward it to the nodes on the edge. Okay, so on the edge side, we actually also keep the idea that we want to run the whole stuff inside the process, so make it easier to manage. So currently we have the following modules, and for different user cases, users are able to disable the module if it's not usable in that case. For example, if some user like running KubeEdge in a CDN cases, they may not need the device management functionality, so they don't need that. All right, so for the Edge Hub, it's a symmetric implementation compared to the Cloud Hub. It's dealing with the bidirectional communication. Okay, so Meta Manage here is actually a node level metadata persistency. All right, the HD is the lightweighted kubelet implementation. So basically, we are actually reconstructed of vanilla kubelet modules to remove the cloud provider storage implementation. Yeah. And device string here is actually to deal with the device status updates between cloud and also persisted on the edge node for the applications to process. The event bus is actually the client implementation to talk with the MQTT broker. And also the edge mesh here is like I said, it's a multi-layer functionality to deal with both service and as well as the CNI. So the difference between edge mesh and the CNI here is that CNI, so the KubeEdge in the KubeEdge project, we don't want to rebuild the CNI, even though the current CNI implementation cannot deal with cross private network communication. We want to make it that is that the existing third-party CNI, they can still deal with the cross-node communication inside one network. When it's cross-subnet communication, each mesh will help to forward, like use the, for example, P2P terminal, or we rely on some gateway nodes to forward the packages. For the monitoring, currently we support the standard metrics interface. All right, so that's basically how KubeEdge works, and I will quickly go through the few updates about latest KubeEdge release. So we just have our 1.4 release, and by the end of last week. So since last week time we met, we improved the component config. So now you can easily use declarative, basically the Kubernetes style of API to config KubeEdge components. And also we provide the minimal config and also the full default config command to help generate config file with defaults. For the node setup, we provide the Edge node automated registration, and also automatically enforce the TLS between Edge nodes and the Cloud Hub and CloudCore. And also we introduced the automatically certificate rotation, so users don't need to worry about the certificate expiration in the edge computing cases. We also have a installer tool. It's called the KubeEdge. So again, we are reusing the idea we have in the vanilla Kubernetes in the data center. The enhancement recently is we added the CentOS support, and especially we added the Raspbian support. So now user can easily use one command KubeEdge and join to set up a node in the Raspberry Pi. Also for the cloud part, the high availability improvement is that we implemented active standby mode for also integrated with Redis gates. Another thing I want to highlight here is that KubeEdge itself, the CloudCore, even it just have one active instance. At the same time, it can manage up to 1,000 edge nodes. So we think it's a good status for now, and the community keep working to improve the scalability. Okay, and then another thing is that we improved the reliable message delivery between cloud and edge to make the whole system more stable. And for container runtime, the community verified the integration of CRI-O and the cutout containers, and also both the x86 and ARM architecture, especially ARM v7 and v8, are verified. And for the observability, users are now able to use kubectl logs to collect all the logs from the pods on the edge node to the cloud. Basically to the where you run the command. And also for the metrics, we support the Kubernetes metric server for collecting both those in the cloud and those in the edge. So basically, KubeEdge, the idea is that we want to extend vanilla Kubernetes to make one cluster able to manage both cloud nodes and edge nodes. All right. Another big improvement in 1.4 is the device management. So we actually modified a bit about the API, so added more, improve the capability of customizing the industrial protocol, and also added the functionality for users to process some data on the edge. For example, we know that in many cases the IoT device may produce a lot of massive data. We need to use some filter to reduce the data and fetch the one we want. So with the data section and the data pipeline integration, it's easy to do that. And also for the basic properties, we moved the property visitors from device model to actually the device instance API. So because we think that we found that in many cases the device properties may be different in different on different device instances. All right. For the community release development, so currently KubeEdge is doing a release every 3 months. So basically, it's we are following the semantic versioning spec, and community. So actually, we're also doing quite Kubernetes way. We will review the feature planning in the beginning of each release cycle, and also we will do the code freeze when it has it's 2 weeks away to the final release of each release cycle, and accept only bug fixes and document updates until the release out to make the release stable. And another thing I want to highlight is that because we know that the underlying hardware architecture reality, so currently both x86 and ARM are supported as a native architecture through whole release lifecycle. For the code is actually very general, right? From the build to test, ship, and run, we have the ARM-based CI, and also we have the cross-build, cross-testing scripts and test cases. So a little bit about the community updates. Currently, we have around 400 contributors all over the world, and more than 130 contributors submitted code. And we also have the over 30 organizations working inside the community. It's covering the cloud provider, IT service provider, hardware vendors, and also the IoT vendors and academics. And also KubeEdge community currently is moving to the SIG-based governance model. So recently we started 2 new SIGs. One is device IoT SIG. That SIG is more focusing on the device management cases on the edge, and also responsible to support the and improve the extensibility of integrating more industrial protocols. Another is the SIG MEC. It's focusing on improve KubeEdge to become a relevant reference architecture of building a infrastructure for 5G and MEC. And currently, the SIG is collaborating with FTUG Telecom User Group and also the RFH projects. We have two relevant blueprints inside Akrino. Akrino is the project under RFH. All right. So this here we have a few contributors here. So we can find that the community member companies include the cloud providers, IoT service providers, and we also have the telecoms and also the hardware and the IoT vendors. KubeEdge itself currently have more than 20 adopters, and so the biggest use case is the China Highway provincial electronic tolling system. It's currently managing more than 50,000 nodes, so very impressive. All right. Yeah, this is more a little more details about the use case. So basically, so actually in China, the highway system is very complicated, and also the tolling system is highly distributed and have in total there are more than 100,000 nodes to manage. So currently they use the KubeEdge and in the cloud the Kubernetes to manage the whole infrastructure, so they can do training in the cloud to get the model to recognize the car number plate, and also ship the models to the inferencing model to the edge, and the edge nodes will recognize the car plate and also trigger the electronic tolling. All right. So one of the progress currently is that the system is dealing with over 300 million data records per day, and for the car passing through the toll station, it improved from 15 seconds to 2 seconds, and for a truck, it reduced from 29 almost 30 seconds to 3 seconds. So very impressive. And currently, the end user are still doing more work to adopt deeper KubeEdge to introduce the vehicle corporate system, and also provide the central video cloud, and improve the AI algorithm to make the whole system smarter. All right. So future plan, we still want to improve the observability and maintainability. So and simplify the remote debug from the cloud to the edge, and also improve the cross subnet communication. So currently the implementation is relying on the gateway nodes. In the future, we want to implement with like P2P tunneling technology, and also like other technologies like SD-WAN. And also for applications, we are going to provide the centralized security, basically the identification for authentication for the applications on the edge. From community-wide, we think we're currently applying for CNCF incubation. It's still under voting currently, and we want to improve a better contributor experience, and also the have more contributor events, and we also organize more the events, and also we may do more cross-community collaboration. So these are the useful resources about the community. All right. Then I will share with the demo. Because of the time, I recorded with the video. Okay, so hold on a second. All right. So the first demo is the device management. That's actually this developed against the device CRD v1 alpha 1, but it's I think it's simple enough easy enough for the all the attendees to get the idea that how KubeEdge API the device CRD works, and can manage the devices on the node. Because this one, in this case, we are actually connecting the device with wires. So we actually the mapper here is converting the MQTT to the I/O of the Raspberry Pi. So it's a little bit different to the real world. We are actually converting to from a MQTT to a industrial protocol. All right. So in this deployment, we use kubectl to get nodes, and we can find that we have one node on the edge. It's a Raspberry Pi, and that time was based on the KubeEdge 1.17. Yeah, and we have the traffic light part. This one is actually a device mapper implementation to deal with the traffic light management, convert from the CRD, change it to the light, to the GPIO GPIO output. And here by default it's the off. Right. So let me just go a few seconds back. Sorry, here. Okay. Yeah. So we introduced the device twin section in the device CRD status. So the twin, basically they have two parts. One is desired, another one is reported. So simply you can change the desired from off to on, and it will turn on the corresponding light to on. Yeah. In this case, we actually coded the GPIO details in the mapper. So from the CRD side, it's very simple. Okay. All right. Save it, and then you can find out the red light is on, and also we can change to change the green light on, and just to save, then the green light is on. And also we can change like the yellow light, or we can just turn off the red light, and also turn off the green light. Yeah. This one is very simple actually, because that's more IoT relevant. And the load is how you design your mapper and how you deal with the device protocols in details. so I'm not going to through too much details here. If you have any questions or you want to know more details, you can also enter the examples repository under KubeEdge GitHub. You can find all the code there. All right, another one demo here is the facial recognition. All right, so here I'm also using the Raspberry Pi as a edge node, and for the camera I'm using the latest. It's a 8 million camera, 8 million px, I think. Yeah, and yeah, let me go through a little bit quicker. Okay. So, all right, here on the right is actually a kubectl terminal, and on the left it's I'm turning on the remote view of a Raspberry Pi node because we want to view the video there. Okay. So I trained the model in the cloud, and it's based on the CPU. So Raspberry Pi, we have the CPU there. We can rely on CPU to do the facial emotion recognition there. So here we can find I trained the application and also uploaded to .com, and also sorry. All right, the status bar is kind of covering. All right, so because we also want to preview the emotion recognition, so I set up the environments to display the video window, and also I mounted the corresponding hardware on the Raspberry Pi. So made the container able to fetch the video frames. All right, then let's apply this YAML. Okay, you can find out the video window is out. So you can find it's actually recognizing the emotion rapidly. Okay, so and also a little bit details inside the image. Actually, we have the trained models inside there, and the underlying AI framework. We used Paddle here in this time. Paddle is a open source AI framework. It's kind of equivalent to the TensorFlow. Yeah, actually, you can find out the this image. It's actually the image size is around 500 megabytes, and most of the space is used by the base image. And for the model, here it's actually a very small model. It's only about 80 megabytes. Yeah. All right. That's all about the demo. Because it's online tutorial, so we don't have a very good interaction experience about trying it out by yourself. But please feel free to ask any questions here, or even joining the community to ask questions. We are the most of the community vendors members. We are available on the Slack. Let me share the community resource again. All right. And while this resource sharing, I will check if there's any questions. All right. Oh, so maybe I need to stop sharing and then answer the question. Okay. Yeah. Let me repeat the question first. From Alexander. Hi, is EdgeHub a WebSocket client or server in regards to the Cloud Hub? In other words, is it who initiates the WebSocket connection? All right. So actually, Cloud Hub is the WebSocket server because in the cloud we can easily get a load balancer or a floating IP to expose as a service. And for each node, when it spinning up, it will send a request to the Cloud Hub to initiate the WebSocket connection. So it means that EdgeHub is the WebSocket client, and the Cloud Hub is the server. All right. Another question from Alex. Thanks for the tutorial. I was wondering, may you tell us more about the CRD abstraction provided for device in the KubeEdge? Thanks in evidence. Thank you for your question. This is a very good question. So actually, we changed a little bit on the device CRD in latest 1.4 release. And latest update, you can actually find out either on GitHub or from KubeEdge community website. The KubeEdge community website is kubeedge.io, and KubeEdge GitHub is actually github.com/KubeEdge, and you will find the detailed CRD abstraction there. All right. We are running out of time, so I will end my talk now. I can see a few more questions there. Thank you for your joining. Please ask your question in the Slack channel, and I will be answering there. And also there we have a few more other community members there. All right. Thank you for your listening.